Hello, YouTube. This is the last show in the series, and we're live in Royal College 667, except not by the time you're seeing this. And we're going to do some naughty problems. So let's have fun. Okay, so this is a variation on the theme of diff that we've been working with. And I was kind of, so some people took took the bait and actually went and raided. I mean, I saw comments in people's solutions where they were actually explicitly saying, I got this from this this tutorial solution. This question was really intended to work the fact that it was an open book assignment and that most of what you needed was in past work that we'd done. And I was astonished at how few people did that. I mean, an awful lot of this problem, there were an awful lot of marks available for people who could find their way to where we'd done it before and copy and paste. So that's an important lesson, that this is an open book test. I will give you, the best part of a month to find your way to the things you need to get stuff done. And yeah, okay, it's one of those things where it's partly I recognize in some of the things I saw in front of me the presence of exam technique learned at school. And do you know, it's actually my job to make that not work at university. I'm terribly sorry, but that's what they pay me for, right? Is to make sure that Pavlovian conditioning does not work in exams. So there's a bunch of things that happened. Right. There's another thing that's important to say is I've got all of this machinery. Let's just whiz through. We've got numbers made from spuds on a lemon. And we've got all the stuff about plus, mult, max, all the monoid structure, all the rig structure. I don't know quite why I left choose in here because it's got nothing to do with this puzzle. Except possibly as a reminder that we did something involving choose that was very similar that you might want to pay attention to. And then there's this sum fun below thing, which is this higher order function. It takes a function, so this function f as an input, and it applies f a bunch of times to a bunch of numbers, all the numbers below n. It feeds all of those numbers to f, and whatever comes out, it adds up. So in that sense, it's an awful lot like integration. You got some, maybe I need to point my, well, the moment I'm sharing, I'm not going to do anything that's extremely detail oriented, so maybe you can just see it from a thumbnail. You got some picture like that, you got some curve, and what we are computing is not exactly the area under the curve, but we're adding up a bunch of chunks. Yes, it would be good to so it's something that is close to integration, but in a kind of discrete sort of way, rather than the continuous sort of way. And in much the same way that the notion of diff you're being asked about is not the infinitesimal derivative that you learned at school, but is nonetheless a related differential operator. So you have formulae, and what we've done here is we have added sum fun below and shift explicitly to the language of formulae. So remember that a formula is a lump of data which describes a function from numbers to numbers. And evaluate is the thing. If you read the type of evaluate, if you kind of group the number arrow number on the that's on the right, what we're saying is evaluate takes a formula in and gives you a function out. So it's a little programming language. And you can see that little s sum fun below wants a function, and big S sum fun below gets a formula. And we can see evaluate tells us how to turn a function into a formula. So, so the definition of evaluate, which is well worth a read. I mean, one of the things I really, really need to get across to you folk, I need to teach you to read. Now, you all can read. It's just that some of you are not in the habit of doing so. And it's important when there are problems involving definitions that you read the definitions. They're in your face for a reason. And they tell you important stuff. So you look at this data declaration of formula, and it just says, there's a thing called sum fun below. There's a thing called shift. You don't know, just from seeing that they exist, what they mean. But when you look at how evaluate works, that is telling you what they mean. There's a program that says, this is how this kind of formula turns into a function. That's giving you the meaning. You need to learn to extract that meaning from the code which is there, right? It's not stuff that is book learning. It's not stuff that comes from lectures. It's, here's a new thing. Here's what it means. Get the hang of it. And at university, that's a completely legitimate thing for me to do. I'm, dropping people in. It's what Fred and I do to each other all the time. And it's what we do to you too. So this is telling us that sum fun below Q evaluated at N is going to do the sum fun below operation to the Q formula. So basically, Q describes the curve, and we are going to compute the area under it in lumps. Okay, there's a whole bunch of other stuff that we'll get to. So, question asks for the forward difference operator. And again, those are words that we have used in lectures, and there have been a couple of different variations on the theme of formula where we have defined a forward difference operator. Even then, it's not necessarily the case that you need to know what those words mean, because the very next part of the problem is telling you what on earth this diff thing is supposed to do. right? It's not just write a random program. It's write a very non-random program that is supposed to do a particular thing, and we're telling you precisely in logic, not in English, what this program is supposed to do. And it's a massive clue. I'm going to kick Fred off on this now, is that if you don't know the answer to defining diff P, trying to do this proof will tell you the answer.
And conversely, it's a really bad idea to define diff P fully somehow and then try to do the proof afterwards, right? I mean,
yeah, I saw lots of people defining diff P and not even giving the proof a go. I'm just sort of guessing random stuff for what should happen with some fun below and shift. Usually the shift guess was right. Usually the sum fun below guess was hopelessly wrong. Occasionally the sum fun below guess was only slightly wrong. And my heart bled, but I didn't give any marks. So do you want to have a,
okay,
how are we going to kick off?
Should I try this?
Yeah.
You might have to help me a little bit.
I might have to help you, but you think out loud.
Yeah. Okay. So as we said, we are kind of going to do these two not in isolation, but in parallel in some sense, right? So the first, so we can't, even though we said you shouldn't do diff before you do the proof, it's of course also the case that you can't prove properties of diff before you have actually defined a little bit of diff, right? There's no way I can prove this if diff is completely undefined. So I'm really going to do it in tandem, right? And there are some things I can do without thinking too much. So diff is supposed to take a formula and produce a formula. And it could do something simple. It could do and PP or something like this, but that's, sorry, plus PP or something like this, but that's very unlikely to be the right thing, right? So just by the, I guess you've seen forward difference operators before, and usually we actually have to look at the P to see what the operator is, because it can be different for different P's, right? So I think the first thing I would like to do is to look at P, and it could be that I need to do this recursively for smaller P, so there's no harm in just kicking off with an inductively P, I suspect.
That's the only game in town.
If I forget to do it, then I would realize it later and have to just go back and add it in, but I'll just defensively add it now. And then I'm going to say from P, because I need to look at P, right?
Yeah, you get a bunch of this stuff. Now, while Fred is doing the renaming, I would invite you to think about how this proof is going to go. Remember to play the game, it's a transferable lesson, to play the game, why is it stuck? So, you know, why is the equation that you're being asked to prove not true already? It's because not enough computation has happened. So the proof technique that you need to deploy is to kick it until it computes. And in order to make it compute, you need to, it's not magic, you don't guess, you look at how the functions in the problem are defined. So there's two things we could do induction on. There's the formula P and the number N, and which of the two you ought to pick depends on how evaluate and diff operate.
And strictly speaking, plus as well.
And strictly speaking, plus as well. But that's a
later problem.
Yes.
Right? So
a
plus,
right now problem is what's going on the left-hand side. What does evaluate look at primarily?
Right. So I just go up and look at that. Right.
Yeah. You might want to just do a reverse search rather than, because there's a lot of it about.
Yeah. Okay. So I say that evaluate is looking at P, and it never looks at the number, so we are not stuck because we are making a distinction on the number here on the left, right? The number is uniformly n, and then in shift we change it, but we are never making a distinction. So evaluate really needs to know what the formula is to make progress, okay? And diff, we also said it was a good move to look at the formula. So everything in sight, more or less, is stuck because we don't know what the p is here, right? Diff p is stuck because of that. That disevaluate is stuck because we don't know what diff p is. Disevaluate is stuck because we don't know what p is, and disevaluate is stuck because we don't know what p is. So really, no-brainer, we should look at p, right? And again, since diff p and evaluate are doing inductively p, we should also do inductively p, so we can follow the same moves. When diff p makes a recursive call, then our proof can use the induction hypothesis. So say inductively p, and I'm going to say from p, and that's going to give me all of these cases.
With really disastrous made up names.
Yeah.
But
so maybe we fix the names as we go along.
yeah.
Okay. So the next thing I can do is I can look at these and let's see what happened here. Right.
Yeah, I would put spaces between the cases.
Yeah, let's do that.
Let's just space it out so that it's not complete.
Right.
Solid.
It doesn't look so overwhelming.
Yeah.
So we have a bunch of cases. And now, again, we have really no hope of, if we look at why is it stuck? Well, I guess we can test this, right?
Yes, I think that's very much worth doing.
And that's going to give us as much computation as we can. So I'll say test. And okay, didn't like me doing that line break, fair enough. So I'll test that. And then I get a slightly nicer goal, right? So the evaluate here on the left has said that, well, when you evaluate the variable, you plug in the number you have for the variable. So that just became S of n. And when you evaluate n, x here with the value n, then we just get an n. So what we see that we need to define diff of x so that when we evaluate it at n, then we should get, and add n to it, then we should get S of n. So we need some way of turning this so that this plus n is equal to n plus 1. Well, seems to me like we should define this to be the number 1, right? So say that this, and it has to be a formula. I can't just say 1 here, that doesn't make sense. But thankfully, we have this num formula, which stands for the number, right? And if we look at the evaluate of num, it's just going to ignore its argument n and return m, right? So it's the function that's constantly m. So here I can say num 1, and 1 is s of 0. Is that how we call it?
I did get more than no solutions where the derivative of the variable was given as the constant 0 instead of the constant 1. Defeat snatched from jaws of victory.
Right. Okay. So
I
then,
should, of course, also mention the importance of you know, the lesson we call plagiarism 101, which is that if you're going to copy somebody else's solution, pick someone who can do it. And so
okay, so now I defined what diff of x should be. It should be num of 1. And then I go down to finish my proof, and I see that I don't have anything to do anymore because the equation is just true, right? So by saying tested, the left-hand side has evaluated to S of n, and the right-hand side has evaluated to plus 1n, which just computes to S of n. So that was a nice surprise. I can delete this. And that case is done, right? then let's do this one. So the first thing I'll do is I'll rename this to M. Okay. And then I see what I have to do. So I need to prove that if I evaluate, okay, so again, I shouldn't do too much thinking myself. I'll just say test first. And that's going to compute as much as it can. So the left-hand side really is just M. And now I see that I need to define the diff of num of M in such a way that when you evaluate it and add M to it, you should get M, right? So that really doesn't leave many options. If I choose anything but 0 here, I'm going to be in trouble, right? Right. So far we've just picked numbers, and later we're going to see that that's not going to be enough. But these are kind of the simple base cases where we can just pick numbers. So let's do that. So here I said that the diff of num M should be num of 0, right? So again, kind of familiar from derivatives, right? If you take the derivative of the variable, you get 1. Take the derivative of a constant, you get 0. Okay. Definition, fine. What do I need to prove? Well, nothing anymore. It's just true. So there's nothing else to say. Okay. Then let's do the next case. Anything to say about that case?
About the constant case.
Yeah.
Well, again, I mean, the goal tells you what to do, and it shouldn't be a surprise. I mean, so all of these operators are like, what happens to the output when you change the input? And the derivative you're used to is what happens to the output when you change the input infinitesimally. Whereas this is what happens to the output when you change the input by 1. So it's going to be similar, but not exactly the same. However, what happens to a constant when you change the input is always hee-haw.
Okay, so let's look at the next case. So it's the add case, and I've just tested the equation to make it compute a little bit. So I see that what I've left to prove is that if I do a plus of evaluate Q S of n and evaluate R S of n, then I should get a plus of the diff of add QR and evaluate. Okay, it's a bit hard to see this.
Put a new line at the equal sign.
Yeah, am I allowed to do that?
Yeah.
Yeah.
As long as you indent.
Yeah. Didn't quite work. Okay. So what could I hope to see here? Well, there are a bunch of recursive calls I could see, right? So I know that this thing should be the same thing as, maybe, can I do that even now? So I'll do the recursive calls before I have defined the addition. Was that a bad idea?
Not crazy.
So I'll just say, well, I know that I can do it for Q. So I'll copy this.
Yeah, that's not going to help. But you could do so from with this equation won't do a rewrite or anything. It only rewrites variables.
Right.
So you need to do a by root.
Right. Okay. Right. So then I have to think a little bit myself, right? So I'll just copy this thing. And then, because I know what...
You know what the left-hand side ought to be.
What this should be, right? This should be... this. With a Q. And this should be the same thing with an R.
The other thing, of course, that could happen and will happen for multiplication is that we're just going to go and steal it from some previous bit of work that we already did. Right. So this is hardly news. Right. Yeah. It's,
no, didn't like that.
you need an extra set parentheses around. So the thing is that the rules are like type constructors and data constructors. They begin with a capital letter and they have the same syntax. Which is why it was awkward that the first rule you encountered was root, because we did a bunch of equations before we did propositional logic.
Right. Okay, so let's see. So I now have two sub goals because I want the left-hand side to be equal to this thing in the middle, and I want the right-hand side to be equal to this thing in the middle, right?
Yeah. The first sub goal is easy by construction.
Yeah. So here I can now just say, what do I need to say?
Under
plus.
And it's done because once you take the corresponding inputs to that plus, they are just exactly the induction hypothesis, which is how come Fred came up with that thing in the first place.
Yeah.
Right. And now we're left with a little jigsaw puzzle where we can see on the right-hand side of the equation, there's this thing, thank you, Fred, that we don't know yet.
Yeah.
But we can see how it has to relate to what we do know.
So on the left-hand side, we have a bunch of pieces, right? And if we already have that piece on the right, then we don't need to include it in whatever this is producing, right? So I can see that I already have a value at Qn here, for example.
Yeah.
And I already have a value at Rn. So what am I missing?
I would throw an extra space on the left-hand side. The left-hand side could enjoy being put over two lines.
Yeah.
Yeah. Like that.
Yeah. Okay, so I have already accounted for these two pieces, but I'm still missing these pieces, right? So I think if I just define the diff of an addition to be an addition of diffs, then I'll get there, right? So this is diff of Q, add diff of R. Okay, let's see what I still have to prove. So this time the thing didn't go away, but I can now test it again.
And that's enough.
And then it goes away. Yeah.
Because swapping middle of 4 is in the library.
Okay. Let's see if we can do multiplication. So we start with the renaming. This is Q. This is R.
Yeah. Now here, I was actually shocked by how many people just reflexively punted out the product rule that you learned for infinitesimal differentiation in school. It was just like, I pressed a button that was already installed by your school teachers. And the thing that happens when that button gets pressed happened, even though it's not the right thing because I'm asking for something that's slightly different. And yes, I do that stuff deliberately. No.
Yeah. Okay, so let's just take it slowly and see what we need to do. So we can follow the same first strategy as in the addition case, right? Where the left-hand side is a bunch of evaluate of S of n, so we know inductively what they should be. So we can just say by root. So I'll just copy the same root.
Yes.
And change some pluses to mults.
Yes.
Right?
The outer plus should be a mult.
Right, but I should also say by root. And then that was a mult. And then this thing here is what this should be. And this thing here is what this should be, right? So if I do that, I get these two sub-goals. The first one is just under mult. And the second one, we actually have to do some work. So let's see if we can line this up a little bit again. Oh, can't use tab for that. Oh, what happened?
That's the other thing we keep doing in these double acts, making each other use keyboards we're not used
to. Right.
This will be.
Can I undo this? I can't. Okay, let's just go back to this state. And we said this one was under mult. And here I wanted to line things up a little bit nicer. Okay, what do we have? So on the left-hand side, we have this multiplication of these things. And on the right-hand side, we have an addition. So we have, right, so what should this left-hand side be? We could multiply this out by another root, right? Do we have this in the...
Yeah, you have distributive laws are knocking around. But yeah, you can see when you multiply it out, you're gonna get this thing here. Yeah. But you're going to get 3 other terms, not 2.
Yeah. So we're going to get this times this, plus this times this, plus this times this, plus this times this, right? And that last one we already have, but it looks like we should define this thing to be the addition of the 3 other terms, right? So let's see if we can do this. Say this is add of something, something, something. And what was the first thing? It was the mult of diff of capital M.
Capital M, mul.
Yeah.
Mul, not mult.
Mul.
Terrible person.
Okay, so that was diff of Q times R. And then I wanted diff of, sorry, another multiplication of diff, well, Q times diff of R, I suppose.
Right, so these are the things you usually expect, but there's a third term.
Which was a mul of diff of Q and diff of R, right?
Yeah. And that that mul of diff Q diff R in infinitesimal differentiation, that's vanishingly small. That's an infinitesimal, but we're not doing infinitesimal differentiation, and that term is going to survive. You also see that inductively, we know that you can take that last term and group it with either of the other two.
Right, you're saying that the order here I defined this doesn't really matter.
Well, the order doesn't matter, but yeah, you can turn it into two terms instead of three.
Right, so I have a diff of Q time multiplied by something in two cases.
Yes, so diff of Q multiplied by R plus diff R, and R plus diff R is a thing. It's shift R.
Right.
Or you can do it the other way around.
But I guess I could also not be so clever and see what happens.
That's also fine.
So
that's also fine.
I'll go down here, and now I can try. So now I know what this thing is, so I can hope to test it to see if it computes a little bit more. And it does, but it looks kind of messy.
Yeah, but it's gonna just be algebra.
Yes.
So tell you what, why don't we have a halftime break and we'll just do the boring algebra and get to the fun bit when you come back.
Yeah.
Okay, it's 5-2. So reconvene 5 past. Let's pause the recording.
Yeah, you can do that.
Can I? Hope so.
Done it before.
Welcome back. You can see we didn't quite finish the algebra on this case, but we are going to win. We have, in the immortal words of Eric Morecambe, all the right things, but not necessarily in the right order. However, let's get to the fun part, which is the next case. We're going to win. We just have to do the right bits of associativity and commutativity to get that thing to sort out.
So I think it's a good thing if you're faced with this is to ask yourself, is it sensible or not, right? If art says proven, fine, you're happy. If you have to do a lot of work, then it could be because there is a lot of work to be done, or it could be because you're trying to do something impossible. So it's good to pause and think, do I actually believe this or not, and not just blindly bash things in.
Yes.
But in this case, we do believe it.
Yes. Don't always rely on your instruments. You know, a pilot flying a airliner from Edinburgh Airport to Heathrow has all kinds of electronic guidance systems, but can also look out the bloody window and follow the M1. Yeah.
Okay, so let's leave this one for now. That's also a good test strategy, right? You don't have to finish this case in order to move on to the next case. So you can come back to this when you have more energy. So let's do the next case. So it's the sum fund below case. We haven't defined diff of this yet. We're trying to figure out what it should be. So I'm going to compute as much as possible by test. And then I see that my left-hand side has turned into a plus of this and sum from below evaluate blah, blah, blah. And my right-hand side looks like this, right? So again, I have the same kind of term here on the right. So if I define the diff of this to just be Q, then this will just be true, right? So then we don't have to prove anything here anymore. So that just
Yeah. So that again is key message is trying to do the proof is the good way to figure out what the program ought to be doing. So I saw a lot of guessing and not enough proof. And if there had been a kind of exploration and a letting the machine tell you what it needs, then you're in much better shape, rather than thinking, oh, I ought to know this, I don't know this, what would be plausible, right? You know, maybe you were pretending to be Chat GPT, maybe you actually used Chat GPT, but it's not going to work. Some people gave us shift Q as the difference of some fun below Q. Good guess, nearly right. But it's Q itself. And if you look at the definition of some fun below, why don't we do that?
oh, it's some rather than some. That's fine.
Yeah. You can see what's it doing to get from some fun below fx to some fun below f of suck x. It's adding on f of x. It's adding on the very function it's summing. So that's that is it telling you what the relationship, you know, some fun below is all about forward differences. It is the notion of integration that corresponds to the very notion of differentiation we're defining.
Okay. Let's see. So we only have one case left, right? The shift of Q. And I've tested it to make the left-hand side compute. And the right-hand side is still stuck because I don't know what this is yet. That's what we're trying to define, right? But okay, so again, here on the left-hand side, we know something inductively, namely that this thing here should be the same thing as, because it's an evaluate Q of a successor. So it's far to go up to the top now. So we know that that inductively should be something like this, right? So
Yeah, cool. Yeah.
so I could again just by hand say that, well, I know what the left-hand side is inductively. It's going to be this thing with a Q.
And suck n instead of n.
And right, and I'm doing this for suck of n. So when I peel off one suck, I still have a suck n left, right?
Right. So another thing to remember about induction, that variable that you're going inductively on has to get smaller. All the other variables can be whatever you want. And here we want it to be slightly different.
So we are doing induction on the formula, right? So we have gone from shift of Q to Q. And Q is smaller than shift of Q because there's one more thing here.
Yeah, so it doesn't matter that we're making the number bigger. What's important is that the formula gets smaller.
Okay. And then we only get one subcase because the left-hand side was equal to this just by the induction hypothesis, right? So then we can see what we have. Okay. And it looks like we basically have no. Right. So again, this bit is just what it is. We can balance it out. We have it on the left, we have it on the right, so we don't need to worry about that. And we need to define diff of shift of q in such a way that when we evaluate it at n, we get the same thing as if we evaluate diff of q at s of n, right? But this move of saying evaluate something so you get something else at s of n, that's exactly what evaluator shift was doing, right? So I think if I go up here and I define this to be shift of diff of q, I think that might do it.
So lots of people guessed this and they got, well, I don't know whether they guessed it, but whether it made sense. But that was a mark that was frequently awarded.
And then we go back down to the proof and we see that there's nothing left to prove because it's just true by definition now, right? So we can just get rid of this. And unfortunately, it's not all proven because we still have this bit of algebra left, right? Which we'll slot in after the lecture, I suppose.
Yeah.
Okay, what's next?
Good question. I wonder how much more of this we ought to do. Except to say that we're interested in defining this notion of degree, and it is exactly the same as the notion of degree that we had in the relevant tutorial. So this was done fairly well. So this is going to be, well, this is going to be inductively P. And then from P, for sure. Incidentally, we're going to want to prove this. This is just by way of saying that the notion of degree does the right thing with powers of the variable. It should be a surprise to nobody that there's like one variable here. Power E is defined inductively on that variable. There was a there was credit available for getting that far, and you didn't really have to think much to get that far. So I was very glad to give that mark to quite a lot of people. Likewise, we know that this proof is only going to go one way. But now we got stuff to do. Okay. So the degree of the variable is 1. We've seen that before, and indeed that's what is required by, if I do test here, we can see that we need to be so x times, so power 0 is 1. The degree of x times 1 has to be successor of 0. So that's telling us that the degree of x had better be, yes, that's me being a klutz. That's n, not num. It's a formula, not a, it's a bot num, not a, right. So that's handy. And I'll actually, now that I've defined that, hit that again. And here, so there was a thing that came up. So there was a credit for I went inductively. Lots of people got this far. Well, we'll see. We haven't done all of this stuff yet. So the degree of a constant depends on exactly which constant. So this is the point, is that adding up constants which are positive actually gets you somewhere. Adding up constants which are 0 never gets you anywhere. So that's why the degree of 0 is but, whereas the degree of a positive constant is merely 0. Then we got some Q's, some R's.
You did a bunch of this in lectures and tutorials, right? So
Sure.
that's why Connor is not, you're not just making these things up.
Yeah.
Based on experience. And
Yeah.
then it's verified by being able to prove the theorems afterwards. So.
Yes. So then this is done with Max. This is old news. And this is done with plus. And hopefully this, if I again replay this test, I get a little bit further. And now you can see, so lots of people did get this far with b degree of power m showing up. But the extra partial credit was for realizing that because m is smaller than n, you know something about it. So I'm going to copy the whole left-hand side. And then I'm going to replace this thing by what we know it to be inductively. And now I'm asked for this thing. And that was so that actually got the right to middle is the thing. Now here's the thing that you need to have your head screwed on for, is a little bit too much computation has happened on the right hand side, but you can undo it manually. So what we want is for this to be true. Right, so this is right, that's the point, is that this computation actually happened. But if we undo it, then it becomes possible for us to say under B plus to finish the proof. So getting into the state where the induction hypothesis was usable. So I would have given, so it's only when we do this under B plus that the induction hypothesis actually kicks in. But I was happy to award the credit if people showed intent by choosing a sensible route. But lots of people just didn't didn't get there. Okay. We're back at the bone as far as the degree of some fun below Q is. And once you've realized that some fun below Q, that we know that diff of it, well, let's actually look. If we say here, let's do test on this. You can see we want the degree of Q to be 1 less than the degree of some fun below Q, which means we want the degree of some fun below Q to be 1 more than the degree of Q. Again, trying to do the proof about the answer tells you the answer. Now, some folk were terribly enterprising and chose the degree of some fun below Q to be bottom. And that's not the right answer, but it does make this case of the proof go through. So it was I awarded that craftiness some partial credit because it did make the proof go through. It's not the right thing. So here we need to be able to compute the successor of a bottom. And some people just did that by B plussing with successor of 0, and that's cool. I was happy with that. My inclination would be to define B suck. If only my fingers worked. I think this is clean. Right, and crucially, adding 1 to minus infinity does not get you anywhere. Adding 1 to something that's on the chart gets you somewhere. And now we can say that this is B suck of B degree Q. Again, this was stuff that had happened before. And now if I replay this test, I see that I need B pred of B suck of something to be the thing. Fine. And hopefully, if I run this again, we're done. Meanwhile, back in shift land, what do we want? We want the degree of shift diff Q to be the predecessor of the degree of shift Q. So we know that the degree of diff Q is the predecessor of the degree of Q. So what is this telling us that shift does with degree? Very little. The degree of shift Q is the degree of Q. And then if we run this again, that's home. And I don't know whether I can be bothered to finish the rest of this stuff, because it's a copy and paste job. These other cases got done in tutorials, so just steal them. Okay, but that was a question that caused a lot of trouble. So I'm hoping that it's good to have a video of working through it, talking through how to think about it. The important takeaway transferable lesson is that the proof about the program is not an afterthought. The proof about the program is an important clue to what the program should be. That the people who didn't bother with the proof and guessed the program cocked it up. What's more, there's usually quite a lot of credit for even starting the proof in a sensible way. And people who couldn't be bothered with the proof flushed that credit down the toilet. So you know, here we go. This is a brain switched on game. And that's by the way, the other reason why I give you plenty of time to do these things, especially when they are kind of online using machinery. I used to run a module which was all programming, and I used to run a 3-hour exam in a lab actually doing programming. There's no point in assessing programming by pencil and paper, right? Actually, you're learning a skill. You should show that you've mastered the skill by doing it. But you put people in a room and say you got 3 hours to solve this problem. You will notice your nose will, as invigilating that test, my nose was telling me that all I was doing was making these poor people sweat. I was testing not whether they could do it, but how well they could cope with extremely stressful situations. And that was not what I wanted to test at all. So that's why I just stopped doing that kind of exam. I could tell that the results I was getting, the numbers I was getting back from the people were nonsense. No reflection what and the work that was being submitted. It's like, you know, I knew that when these people were calm, they could do it better than that. You know, so that's one reason why I'll give you a decent window so that you can look at it, panic, calm down, come back 2 days later and do it. You know, so okay. I should probably change topic completely. I was asked a bit about Brzozowski. I wonder where that lives. Is it semester 2, week 8? Or was it week 7? Or is it somewhere else entirely? Trying to find a file in my labyrinth is sometimes disturbing. Where did I put it? I mean, if I actually go to maybe I'll stop sharing my my Emacs and share my browser instead. So here's Zoom, share, Firefox. And now I can go here, and there was a tutorial on Brzozowski star and pair. Unfortunately, now we're watching in black and white, but lots of people were asking about this. Well, so first of all, maybe I should make the font bigger. Let's remember what the overall mission was. We were trying to write a program which would process a string to see whether a regular expression likes it. And we're being driven by what's in the string, right? The string is either empty or it's got something at the front. So if the string is empty, we want to check whether or not the regular expression likes nil, likes the empty input. And that's what we do with nullable. So it's, you know, does it like the empty input? And this turns out to be not just any old function. It actually turns out to be a map that preserves rig structure from the regular expression rig to the Boolean rig. So you can see that fail, which is the thing that behaves like the zero in regular expression land, turns into false, which is the thing that behaves like zero in Boolean land. Meanwhile, null, which is the thing that behaves like one, turns into true, which is the thing that behaves like one. So message here is when you see this kind of structure showing up, right? One of the reasons I'm trying to teach you about this kind of structure is that you'll find it all over the place if you're looking for it. And it will make your instincts more often or not than not go the right way. So likewise, we are turning or into or and into and. So that's to say, you know, P then Q can only accept nil if both P and Q accept nil. Then we know that any number of R's is going to you know, because 0 is a number. 0 is a perfectly acceptable number of R's. So yes, it's also the situation that I don't know if people on Zoom can see this, but I'll write it big. That R star is equal to empty or R star. And that already tells us that what nullability has to be for it, because it's got to be nullability of null or R star, and nullability of null is definitely true. So there's no choice about that. In fact, all the choices are in one case, right? This case is the only place where we actually do any work, where we're saying, you know, if the thing is supposed to be nullable, then symbols are not allowed. So it's a funny kind of thing here, because what we're basically saying is replace all of the symbols by false, and evaluate the regular expression as if it's a Boolean formula. That's what's going on here. So there's a strong resemblance between nullable and evaluate, which I would recommend that you recognize. Okay. So that's what happens if the input's empty. And then what we're getting at, we're not going to get anywhere about matching unless we can just test if two symbols are equal. So we show that we can check if two symbols are equal. You've got this ensure thing, which is handy. This goes the other way. This turns a bit into a regular expression, which is basically saying turn false and true into dead and alive, right? If we're alive, we're not going to consume any data, but we're not going to fall over. So that's what's going on there. And then Brzozowski, this is published in a paper from 1964, and I actually have hard copy of it from the original journal because the department was throwing it out. I stole it. Right. So the idea is that if we've got a regular expression like one of my examples was this thing, and then we can see there's some symbols in this picture. There's C, A, D, R. And we can see that what we're being asked is if we're being asked two questions at once, namely, is it okay for the string to begin with this symbol? If not, we're dead. If so, we're asking, what does the rest of the input have to look like? So here we can see that the input has to begin with a C. So if we actually get A, D, or R, there is no acceptable rest of input. We've had it. And if it is a C, then the rest of the input had better look like some A's and D's and then an R. So that's the game, right? So that's the crucial thing. Again, down here, specimen solution, knocking around. What we are trying to prove is this. That's what's coming out. So again, it's not necessarily what people are used to, but and it's something in your experience as programmers at work, you will almost never find a customer who tells you as precisely what the fuck they want as I do. So read it, you know. Right. So we're really saying this has got to be the thing that judges the tail of the input, given what the head was. So we've got 10 minutes left and we can work through this. Again, I'm not sure what the Zoom experience or the YouTube experience will be like with the mixture of big screen and pictures. But so okay. the question we're asking is, are we allowed to start with X? And if so, what's the rest of it? To make the original regular expression happy. Well, so if the original regular expression is fail, we're dead already, we stay dead, right? You know, the game was up some time ago. You know, if the regular expression wants the empty input and we're feeding it an X, we're stuffed. If the regular expression wants Y and we're feeding it X, then there's two possibilities. Either X and Y are different, in which case we're stuffed, or X and Y are the same, in which case it's thank you for the Y I was looking for, no more, please. Yeah? Then the usual deal, you know, you might notice, you know, it's a bit like differentiation, that the thing that behaves like plus just distributes. So, you know, does Q or R like an X? Well, it likes an X if Q likes an X, or if R likes an X. And what comes after is whatever comes after in the Q or whatever comes after in the R. So there you go. And then this thing here, this is the fun one, the then case. Let's do star first, right? So does star R like an X? Well, okay. If it likes an X, then we definitely don't have no R's. The X must be at the start of an R. Correspondingly, we must have the rest of that first R, then some other R's, 0 or more R's that are still fully intact. That's why that's that away. And then there's this thing. What have you got? We're basically saying, again, I'll try and write big. We've got Q then R. And there are two possibilities. One of them is that we've got a big long string that chops up between some of it which is Q and some of which is R. And there's an X at the front of the Q part. That's one way there can be an X at the front of a Q, then R. The other situation that can happen is that the Q part is empty and the X is at the start of the R. So that's exactly what we're saying here with this thing. It's that we're saying either the X was at the beginning of the Q and the R was left alone, or the Q was empty. The Q was nullable, and we were at the beginning of an R. So we were left with the rest of the R. So that's why this is the way it is. It's about putting your finger on an X. You got some formula that talks about where where the symbols might be. And the question that you're asking is, can I put my finger on an X such that there are no symbols to the left of it? That's an important thing to do. What nobody told you at school. Well, okay, at school you were introduced to one differential operator. And so far in this in CS103, you have seen two differential operators, neither of which was the one you learned in school. But Isaac Newton, and CS103 is basically a tribute to Isaac Newton. It used to be a tribute to Euclid, now it's a tribute to Newton. Right, so Isaac Newton spent a lot of time asking, how does the output change when you change the input? This thing that looks an awful lot like finding a slope. And the derivative you're used to tells you what happens when B moves arbitrarily close to A. You're letting B tend to A. You're letting this difference tend to 0. The forward difference operator is what happens when B is exactly A plus 1. And this derivative is what happens when A is 0. And it's all about putting your finger on an X, right? A being 0 means I'm putting my finger on something and there's nothing to the left of it. The A's what's on the left, the B's what's on the right. Can I put my finger on an X and with the same stuff on the left and the right? That's your actual Leibniz derivative. So the things you've seen are all versions of this construction, but doing different things with A and B in the limit. So it's and the difference always shows up in the case for multiplication. Because what's going on here is you'll always get the X's on the left in one branch of an or a plus, and the X's on the right. The difference is in the other cases. It's always what happens to the thing that doesn't have the X in it. That's where you'll see variations depending on exactly what you're doing with the B and the A in this divided difference. So here, and that reflects what we want to be true to the left of the finger and to the right of the finger. So here we are saying nothing to the left of the finger. Yeah, so welcome to a world where there are multiple differential operators, and it's an important business. And you might think, you go to high school, you think this is stuff about physics, this is acceleration and velocity and all of that sort of stuff. But no, computer science is full of calculus, because it's all about, if I poke the input, what happens to the output? So again, it's time to stop, but the closing message has to be differential structure, apart from being the machinery behind all of this machine learning stuff that drives us all nuts, it's just everywhere. So watch out for it. Watch out for structure, watch out for logic, watch out for programs are basically proofs that you haven't fully, proofs where you've only written down the mechanism for what to do, not why to do it. But nonetheless, there's a great commonality between proofs and programs, as we've seen working with Ask. I can only apologize that Ask is such a flaky prototype. It was written at top speed in a blind panic in 2020. And it really does need an overhaul. But I hope we've had some fun looking at machines and languages and computation and realizing that there are not actually that many ideas, but there's good ideas. And, you know, go forth into the world and get stuff right. So thank you very much. If you're really unlucky, you might see me in 4th year. You'll see Fred next year. Yeah, have fun. Cheers. Where's the... Stop this recording. Cheers.